What do sound, light, oceans, and slinkies all have in common? Well, I'll give you a hint. So sound, light, and oceans, they all have waves. But what is a wave? I'm so glad you asked. So what is a wave? A wave is evidence of a disturbance in the physical world, or oscillation that transfers energy and momentum. Now, that might sound like a mouthful, and what does it even mean? It means that when you have something in the physical world around us that we can observe, if there's some kind of movement or change, that's the disturbance that it mentions up there, that sends out energy in every direction, and that creates a wave shape. A mechanical wave has to move along some kind of medium. That doesn't mean a psychic, it means something with mass. So light does not need mass because it can move through empty space. But sound needs to hit a particle to hit a particle to hit a particle. It has to have mass involved for it to move along. There are two main types of waves. Longitudinal waves, which are also called compression. These are things like sound, that's how you move a slinky, seismic P waves, and they're kind of a squishing along back and forth. A longitudinal wave you can think of as like a slinky. If you hold a slinky up, and then if you release a little bit, it oscillates back and forth. The individual coils aren't moving very far, but the energy is transferring back and forth. Here we have another example of a pulse going back and forth on a slinky. There it is in slow motion. You can see it goes all the way down and then goes back, but each coil doesn't move very far. Here we have two graphs showing longitudinal waves. The top graph shows several red dots for individual particles. Some places the particles are squished together, some places they're spread apart, but the particles themselves are just oscillating back and forth. They're not moving very far, just back and forth. On the bottom graph, it's labeled. You can see the parts where they're squished together, those are the compressions. The parts where it's stretched out and there aren't very many particles, those are rarefactions. Again, you have red dots for individual particles. They're not moving very far, just oscillating back and forth. But the wave carries along. The wave moves along to the right in this case. That's what a wave is the transfer of energy. It's not necessarily the movement of particles very far, but the energy itself is being transferred. A transverse wave is generally what people think of when they think of waves. It's the up and down, bumpy kind. Now, in a longitudinal wave, we kind of have a squishing back and forth, a compression. It goes back and forth. The energy is going this way in both kinds of waves, but in this way, you have one thing hits another thing, boom, 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 boom. And in transverse waves, the energy is going up and down in this direction. A transverse wave is what you usually picture when you wave a rope up and down, or a jump rope. You can also use a spring and wave that back and forth to make transverse waves, or you might see them on ukuleles or guitars or other stringed instruments. You can see the vibrations in the strings. As the person plays them, they pluck along and the strings vibrate, which causes the sound to form. Here we have a guitar movement in slow motion. You can barely see the strings moving. The top string moves a little more dramatically than the other strings, but you can still see the oscillation. So an example of a longitudinal wave would be something like sound. Something has to hit something else, has to hit something else, has to hit something else, kind of like dominoes. The particles in whatever medium the sound is traveling through have to hit each other one after another. However, they tend to fan out a little bit more and create more of a wave shape, like this. Here we have a model of how a speaker works. A speaker will vibrate back and forth, pushing air particles away. Those air particles will cause vibrations in other air particles, and eventually those air particles will vibrate your eardrum, and your brain will interpret it as sound. Another example of longitudinal waves would be seismic P waves. P is for primary. They're the first waves that hit. So the first waves that hit are the back and forth waves. Then you get your seismic S waves, and those are your transverse waves. So your earthquake starts out like this and then kind of goes into this motion, which makes a big old mess. Another important transverse wave is light. Now light's weird because it acts as both a particle and a wave. We think of it like a wave packet, like a little particle that's made out of a little tiny wave. Visible light is on the EM spectrum. EM means electromagnetic. Now that's all wavelengths of light, most of which we cannot see. This can be things like gamma rays, it can be infrared rays, it can be X-rays, it can be microwaves, gamma rays. All those are all on the EM spectrum, along with visible light, and they're all transverse waves. So what are the parts of a wave? First of all, we have the crest, that's the highest point on your wave. Then we have the trough, that's the lowest point. This little dotted line here, that's your equilibrium point. It's the midline between the crests and troughs. It's the average, basically. The amplitude is the distance from that equilibrium point to the bottom of the trough or to the top of the crest. It should be the same distance. If not, then something's gone wrong. The wavelength is the distance from the crest of one wave to the crest of the next wave. It can also be the trough of one wave to the trough of the next wave, as long as it's the same point on each wave. It's the length of one full wave. Wavelength, Waves also have frequency. Frequency is how often, or how frequent, a wave passes a fixed point in 1 second. We measure it in hertz with a Z. I know I'm bad at spelling, but that's how you're supposed to, it's with a Z. It's named after a person. A hertz is like 1 over a second. The speed of your wave is equal to the wavelength multiplied by the frequency. This is how we write it. This is the Greek letter lambda. It's not just an upside down Y. It's a Greek letter. It's what we use for wavelength. It's measured in meters. Lambda, see? Frequency is this funny looking F. It's measured in hertz. V is velocity in meters per second. So V equals lambda F. That's how you figure out your velocity. Or if you have the velocity, that's how you figure out one of the other two with simple algebra. Looking at this equation, we can make a few inferences. For example, if the speed is constant, like the speed of sound through air, not including humidity differences and stuff like that, or the speed of light in a vacuum, if that's constant, we know that these two have to equal, when they're multiplied together, have to equal that number. So as one goes up, the other has to go down, or vice versa. It's called inversely proportional. Frequency is the number of times a wave passes through a fixed point in 1 second. In sound, the higher the frequency, the higher the note. Here I have a block with 3 metal rods. Each of them, because of their size, will produce a different frequency. Now if you notice, it keeps ringing until I stop it. When I stop it, I stop the vibration. Remember how a wave is a disturbance? It's something moving around and jostling the air around it. So it's going to keep going until I do something about it. Here I have some tuning forks. Now sometimes on tuning forks you'll see little numbers at the bottom and maybe a letter. The numbers are the number of hertz. So let's see this. So this tuning fork has 512 hertz. So hit it against a wooden block. It makes a specific sound. This tuning fork has 384 hertz. So let's hit that with a wooden block. But the sound was much different than the last one. This tuning fork is 256 hertz. Let's hit that one with a wooden block. This tuning fork is 128 hertz. Let's hit with that one. You might be able to see the vibrations just a little bit in there. It's hard to see. Living next to the airport means that I have always airplanes in the background. All of those tuning forks had different frequencies, and that corresponded to a different pitch. Some of them have letters on them, and that's the different musical note that frequency represents. There's gonna be a garbage truck while I'm trying to film. I don't know if it can pick up on the microphone, but it's there. So that's frequency. There's a plane. If it's from a garbage truck, it's a plane. I'm just gonna cry. So that's frequency. How many waves pass a fixed point in 1 second? But what if we want to know the opposite of that? What if we want to know how long it takes for each wave to pass that fixed point? Well, that's called the period. So how long it takes each wave to pass the fixed point. To figure that out, we do 1 divided by a frequency. It's pretty simple. Here's an example. This is Frederick the fly. He flaps his wings 113 times per second. That's his frequency. Frequency is 113. That's pretty fast, by the way. So to figure out the period, how long each flap of his wings takes, we would do 1 divided by the frequency, or 1 divided by 113. Each flap, if we do that in our calculator, takes 0.0088495, there's a bunch more digits, but I ran out of room, seconds. Now significant digits, we had 113 flaps per second, so I have 3 significant digits, so I have 3 in my answer. So my answer would be 0.00885. Remember, these zeros are just placeholders, these zeros up here. If I wanted to write that in scientific notation, I could write it 8.85 times 10 to the negative 3 seconds. Yep. Now, if you remember back a minute ago, I said longitudinal waves were like a bunch of little lines or compressions, kind of like a slinky, spread and squished together, right? And transverse waves were up and down. Then I showed you parts of a wave, and I said the amplitude was right here. Now, amplitude corresponds to the energy of the wave. The energy of the wave will correspond to loudness. It's pretty easy to figure out what the amplitude is here, but how do I figure it out on the longitudinal waves? Amplitude of a wave is the maximum displacement of oscillation in a wave. So basically, if you're pulling a string up and down, it's going to have a bigger amplitude the more you move your hand. If you just pull it up and down a little bit, it's going to have a little bit of oscillation. Now that amplitude is going to correspond to loudness when it comes to sound, and it's going to correspond to brightness when it comes to light. But how do you measure amplitude in a longitudinal wave since it doesn't have that easy up and down motion that you usually see in a transverse wave? Well, in your longitudinal wave, you have areas where things are squished together, an area where the lines or coils or particles are spread apart. When they're squished together, they're higher density. When they're farther apart, they are lower density. So your amplitude is how the closest of the particles in the compression. So how close are these particles in compression? Another way you can easily visualize a longitudinal wave is, like I said, these are areas of high density and these are areas of low density. So if you were to graph that on a chart, high density, low density, high density, low density, high density. I did this freehand, so there's a lot of work. You can see that graphing these areas of density also helps you to visualize what the amplitude must be. How dense the compressions are relates to the amplitude of a longitudinal wave. So the more densely compacted these little compressions are, the bigger the amplitude, or the louder the sound, or whatever. Inside a piano, you have hammers to strike the strings, dampers to stop the vibrations, and you also have pedals that will release all the dampers, or just release the lower dampers, or they will bring the hammers closer to the strings to make the sound even quieter. You can see that that also corresponds, what it does do? Okay. There also, right now we're listening to a plane fly overhead, so we can observe sound. Huh. Looking at this equation, I wonder if I tried to scan this with a barcode scanner if it would work. But how do we know how long it takes for each second? So let me hit it with my mallet. For each wavelength each wavelength, that's not it. Versus a little bumpy dump. That's a weird way to put that. Bumpy dump. I'm on crack. Now that amplitude is going to correspond, gonna. Yeah. Generally think of waves, the movement up and down. Crap, don't do that, help it get stuck. Okay.